This podcast is brought to you by LMU Munich.
Thank you very much to the organizers, Oliver and Dennis, for inviting me to participate in the symposium, and to the program committee for letting it all happen, and to the conference organizers as well. And also thanks to Harvey for making all of the good points in advance, so maybe you'll be able to at least recognize and review them when you see them again here. So geometry continued to be developed after Riemannian geometry and the rise of general relativity. One of the things that people started doing was splitting a metric tensor into a part that involves volumes and a part that involves null cones, irreducible parts, you might say. And this is often interesting to split things into their irreducible parts. In this case, the conformal part of the metric, at least in particular applications, tells you about what light sees, or that's the sort of entity that can do that. And it'll be interesting to keep track of the volumes also. So I'm going to be talking about a critique of geometric conventionalism that was made in terms by Robert Coleman and Herbert Corte, deploying the Ehlers-Pirani-Schild formalism, which is in turn built upon work of Hermann Weyl, who paid a lot of attention to conformal and projective structures. So much of the point that I will be making involves the idea that there are interesting theories in which there are, so to speak, more geometrical ingredients than you could fit into a unique geometry. More or less like the Teve story, except that these are actually quite plausible and natural theories, at least prima facie. So multiplicity of geometries is going to be the theme that makes this work. Now I should say, not everything is going to be multiplied. There's no torsion in this talk. You've learned everything you need to know about torsion, so I'll not need to worry about that. And furthermore, every connection is compatible with some metric or other. So in that sense, we can largely think about metrics rather than connections. The main point is, what do you do with multiplicity? And I will argue that multiplicity thwarts the Coleman-Corte critique of conventionality, which they make using the Ehlers-Pirani-Schild construction. So what is a projective connection? Well, a projective connection is something that you can get by taking an ordinary connection and throwing away parts of it that have to do with preserving the length of a vector, and you merely preserve the direction instead. So if you have the non-affinely parametrized geodesic equation, for example, the part that you can't absorb into that slop term at the end is the projective connection. So if you split a connection into irreducible pieces by looking at the trace, throwing away the trace and so on, the projective connection, which gives you straight lines without parameters on them, is the traceless part. And then the other part tells you about how to parallel transport volumes. So the projective connection coefficients are symmetric and traceless. And this entity is a meaningful geometric entity in its own right, in that it has a transformation law. And the same actually is true for the trace, the volume connection, if you will. That's an independent entity of its own also. So keeping track of these things will help us to think about the relevance to conventionality. Well, Coleman and Corte argued that you can, as a matter of fact, make an invariant distinction between force and geometry, at least within relativistic physics. And part of how they do that involves paying careful attention to projective connections and what powers of the three velocity you get. I'm not going to have to think too much about those matters, but what one does with the connections will be quite important. So they claim to find that inertia and geometry are non-conventional, at least within relativistic physics. What I'm going to do is reconsider the sort of argument that they give using a larger family of physical theories which are motivated by particle physics, and in particular things you might think of if you stare at Wigner's, or even look a little while, at Wigner's taxonomy of mass and spin. I qualify that because they're the weird representations that I'm not thinking about at all, and I'm not thinking about fermions either. So it's just some low-rank tensors. The trick is spin, which has to do with tensor rank, and mass. So massless versus massive is going to be the key distinction. So Ehlers-Pirani-Schild, developing what Weyl did, thought that it was useful to talk about building up a geometry or in particular connection using light rays and test masses. Now you might want to do that because rods and clocks are complicated entities. You need non-gravitational physics like quantum electrodynamics or something along those lines to account for the stability of rods and clocks. So it would be really nice to not have to bring, secretly smuggle in QED in order to figure out your classical theory of gravity. And so if you have test masses and light rays, you have a reasonable chance of doing that. So plausibly, a test mass, or a family of test masses, reveals a projective connection. You get straight lines, you don't get labels on them. And plausibly, a bunch of light rays will give you a conformal metric density. This is a tensor density, determinant -1, weight -0.5. And so the thing that Weil and then Ehlers-Pirani-Schild did in part was to require that these two structures, projective and conformal, be compatible with each other. Basically a requirement that much of your non-metricity tensor vanishes. Now that's not something you can say unless you introduce in addition a volume connection. You can't make any sense out of that covariant derivative without a volume connection. However, the volume connection, the thing with just one index at the bottom, is arbitrary. It doesn't matter which one you pick. So what ultimately happens is your projective connection, your notion of straight lines, is uniquely fixed in terms of your notion of null lines, light rays, if you like, if I may use that term, and your parallel transport of volumes. So in this way, by requiring compatibility, you get a Weil connection with the geodesics you had before and the null cone. So this is very nice because you wind up with something close to experiment on the one hand, light rays, test masses, and made out of physically and mathematically meaningful pieces. So it kind of looks like we're cutting the world at the joints here in developing this sort of formalism. Now, if one introduces a further assumption, namely that your parallel transport of volumes is integrable, then you wind up getting the unique Levi-Civita connection, and then from there you've got a metric up to just a constant factor. So a lot of things simplify. That other trace of the Riemann tensor goes away, and we've now basically got a metric. So this is a nice piece of differential geometry, and where it's physically relevant, it's a nice piece of physics as well. So what is the significance for the conventionality or otherwise of geometry and of inertia? Well, various people in the 70s said this actually doesn't address or doesn't resolve the conventionality problem because, for example, you have to specify what your inertially moving bodies are. And I'm going to be drawing a little bit on what Larry Sklar said. Well, for the last 30 years, Coleman and Corte have said, actually, you do get a refutation of conventionality here. They said it a lot of places, some of them Journal Mathematical Physics, philosophy journals. So you might think that, that's decisive. Well, here I have a really long quotation from Larry Sklar, which I almost agree with. But so Sklar says, well, how do you know what your free particles are? And maybe gravity is a universal force. And if we have a multiplicity of structures, well, maybe the EPS construction will give us rival geometries. So I like a lot of that. However, Sklar would have benefited from massive gravity because there's a certain weakness in the idea of universal forces that is not a weakness once you have, so to speak, a graviton mass term. So universal forces, you recall, are what you invoke to say that the geometry that you observe is not the real geometry. Two critiques that are often made, and not unjustly, are universal forces are not separately observable, so maybe with Occam's razor you should not do that sort of thing, just believe in the composite entity that you actually can see. And universal forces are also gauge dependent. So those are both weaknesses which might, might tempt you to dispense with them. Well, you cannot do that once you introduce so to speak, graviton mass terms. The reason being that the almost universal force that you get, namely the gravitational field, is separately observable, albeit not very easily, and gauge invariant. That means you cannot use Occam's razor because things aren't equal anymore. It's not just the epistemological sum that you've got leftovers of the one or the other of the separate ingredients. So where do you see the remnants of, say, the background geometry? Well, you don't see them in the matter equations, but you do see them in the dynamics of gravity itself. But the effects are very small in that they're, at least prima facie, and it's actually true for the scalar case, they go smoothly to 0 as this mass parameter m goes to 0, which means you can make the effects as small as you want by turning down the graviton mass knob, so to speak. So as long as your massless case is empirically viable, so are small mass cases empirically viable. So you can't empirically refute the massive theories. You can only chip away at them by placing tighter bounds. So when you add mass terms, you have what I take to be a notion of a serious rival. I mean, roughly this. A change you can make in a physical theory that's not crazy. It's a priori plausible, on the one hand, that matters, makes a big difference conceptually, and furthermore, makes a small difference empirically. This is the sort of thing, if you can get it, that makes metaphysics unstable under small changes of physics. And I think that's particularly interesting for philosophical purposes. So my inspiration comes from particle physics, where Wigner classified representations of Poincare group in terms of spin and, most relevantly, mass. What are the relativistic wave equations that one can write down? You can interpret those as the classical field theories that you can write down. And with this taxonomy in mind, you can turn your mind back from 1939 or so to 1914 and say, aha, Nordström scalar gravity, massless spin 0. Now I can color in that slot with a real physical theory. Not a true physical theory, but an interesting physical theory that could have been true. Nordström modified gravity to be compatible with special relativity in the sense of being invariant under the Poincare group. And he had some help from Einstein to do that. Now, one of the reasons one shouldn't believe in Nordström's theory is that it doesn't bend light, and that's actually, you can see pretty much by inspection, thanks to the reformulation of Einstein and Fokker in terms of geometry and the conformal invariance of Maxwell's equations. So you don't get the bending of light, you also get mercury wrong. But scalar gravity survives as a warm-up exercise for general relativists doing various things. And I think it's a good warm-up exercise for philosophers as well. And you can, in fact, actually derive the field equations by assuming you have a massless spin 0 theory satisfying a wave equation. And you discover something interesting. What you thought was a merely Poincare invariant theory, special relativistic, you might say, actually has a larger symmetry group, the 15-parameter conformal group. And that happens because the background volume element that you thought you would observe merges with the gravitational potential. And so it's just that epistemological sum, you might say. So you might simply keep the sum, throw away the separate pieces. And that's an easy way to see that you get the symmetry group. So you could, if you wanted, you could tell a universal force story. I'll assume that we don't want to tell a universal force story and see what we come up with. Well, we've got now a conformally flat metric. Our light rays are just as they were before. Our volumes, however, are systematically influenced by gravity. Okay. Well, I haven't told you a lot about what it means to have masses, and I've occasionally used quantum words in classical contexts, and those are both routinely done in particle physics literature, but maybe not altogether clear. So where does one find anything like massive gravity? Well, you find it first in the 1890s, in terms of mathematical form at least, in that Hugo von Seeliger was worried about Newtonian gravity and cosmologies, in that you can get the potential diverging if you try to integrate over infinite space. So what do you do about that? Well, Seeliger's response was to play with the mathematical form of the gravitational potential. And some of his playing wasn't very elegant, but with some help from Neumann, something fairly nice appeared, involving an exponential decay factor on top of the potential, satisfies a nice linear partial differential equation. So a mass term is basically a term that's algebraic and linear in the potential in question. So you're used to having second derivatives. Well, here's something with no derivatives. But it's linear in the potential. So this is a sufficiently plausible thing to do, I guess, that Einstein reinvented the idea in his cosmological constant paper. Now, unfortunately, he promptly introduced an erroneous analogy to his cosmological constant. That isn't particularly important because I'm not worried about the cosmological constant. I'm worried about the warm-up exercise, which is a priori actually a good deal more plausible. So when did massive scalar gravity get invented? Well, I thought of various times one could give, and they range from the 1890s till 2011. So clearly this is a theory that did not have an ordinary sustained period of development and reflection. Ideally, some of the things I'm going to say would have been said 90 years ago, but I got here as soon as I could and wasn't available at the time. So I think in a case like this, it's quite sensible to envision some kind of rational reconstruction, to think about what people could have and perhaps should have thought at various times in the past. And that can be an aid to our reflection today. Well, the Klein-Gordon equation, massive scalar field, is of course very familiar. What's not very familiar is applying it to gravity. Although with a little reflection, you can see that it's not very hard to do. Hey, why not try it? So that's from the 1920s, to think about the Klein-Gordon equation. Then with Yukawa's work in the 30s, there is increasing recognition of relation between the mass of a particle and the range of the potential that it identifies. So between the 20s or 30s, you can identify that exponential decay factor as the classical analog of a particle mass. It's really an inverse length. Likewise, in the late 30s, you get Procha's massive electromagnetism, which is a quite interesting theory in that it changes the features of electromagnetism conceptually by destroying the gauge freedom. But empirically, you can make the difference as small as you want by just turning down the photon mass. And it also quantizes well, which is, one should always keep an idea for which things stay true quantum mechanically. So I should say almost everything that I'm talking about is classical field theory, but I do also want to be aware of which features are preserved under quantization, and that is occasionally subtle. The higher the tensor rank, the more complicated things can get, though it's not just that fact. So also around 1939, Pauli and Firth, thinking about what kinds of relativistic wave equations there are, noticed that if you have a symmetric traceless potential satisfying a wave equation, you get, well, you can call that massless spin 2. You can also notice that it is the linearization of the free Einstein equations. And so if you're filling in your Wigner taxonomy with physically realistic examples, Einstein's general relativity, you might pencil in to the massless spin 2 case. And they also think about having a massive spin 2. So scalar gravity does not get thought about in 1939, largely because it was, I suppose, already defunct for 30 years. And there would not be a whole lot of incentive to think about something that was clearly no longer viable. But the idea of having a graviton mass is there, clearly available in 1939. So clearly you could have thought of massive scalar gravity in 1939 had you had the incentive. Well, Einstein and Fokker's geometrization of Nordström's theory is very useful for thinking about the fields that we should use, namely break up the metric into a part that does null cones, a part that does volumes, then combine gravity in the background volume element to get an effective volume element and a curved effective metric. Well, you can use the universal coupling story again. It's actually quite similar to Einstein's physical strategy, except that it does actually work. Which is not something that Einstein ultimately believed in the late teens and afterwards. So you can show, it's a theorem from the field equations that matter only sees this effective volume element square root of minus g. However, if you have a mass term, the background volume element is still left over in your theory in that it appears in the graviton mass term itself. So right in the middle of the slide, in the middle of the slide, you see what happens for Nordström's theory. Then you go down below and you see in boldface here the background volume element. So in other words, if you can do long-range gravitational experiments, then you can see what the you can see the graviton mass. So you can't eliminate it. It makes a difference. Furthermore, massive gravity is actually not unique until a few years ago, there was only one such theory actually written down, but it's not too hard to come up with a whole lot more because clever Russians did the same thing to general relativity, which is vastly harder, in the mid-60s. So you can have infinitely many massive gravities that differ nonlinear terms. So here, if you like, is Wigner's mass spin taxonomy with some interesting examples colored in. So massless case, massive case, some examples, and whether the limit is smooth. Well, the limit is smooth for scalars. It's also smooth for spin 1/2, not that that's relevant here. Well, it's smooth classically for spin 1 fields, namely vectors, electromagnetism, Yang-Mills. It's also smooth quantum mechanically for electromagnetism, but not for Yang-Mills. So that's kind of a subtlety. And then for spin 2, well, there's a long, difficult story that ended badly in 1972 and then came back to life around 2000. It's become far more lively since 2010. So it's complicated and quite open. Well, you get a case of underdetermination of theories by data from massive gravity, and that's something that Seeliger already clearly understood. And that, he said, why should we think that Newton's theory is exact? This underdetermination, if you can pretend you believe in massive scalar gravity, also holds under quantization. Of course, we can't believe in massive scalar gravity. We can only hope to learn something philosophically from it. Part of the point of that taxonomy is to suggest something in the vicinity of a limit of inductions that you often see among particle physicists. They're less apt to say, what's our favorite theory, and just think about that one. More apt to say, what more or less serious possibilities are there? Let's think about all of them and then throw away the ones that don't work. And that can be applied to gravity quite compellingly. So from that point of view, if you believe that gravity is general relativity, well, when you see that general relativity is a theory of a self-interacting massless spin-2 field, a natural question to ask, as Pauli and Fiertz did in 1939, is what happens if you add a graviton mass? So until and unless something bad happens to massive spin-2 gravity, it's not clear from a particle physics viewpoint why you should say gravity is a massless spin-2 field. Why shouldn't it be a massive spin-2 field? And there was nothing to be said against that. That was very compelling prior to about 1972. So if you want to know when the particle physicists should have started believing in general relativity rather than suspending judgment between massless and massive spin-2 fields, the answer is the early 1970s, which is, well, not very long ago. And clearly this is a very different story from what we often hear about the history of general relativity and what we reflect upon philosophically. And the sort of story that Harvey was telling about Teves is actually, to some degree, already in one of the important papers about massive spin-2 gravity by Freund, Maheshwari, and Schoenberg, and of all places, Astrophysical Journal in 1969 or so. So it's dangerous to just assume that particle masses are zero. Think of what happened to the neutrino. People treated the neutrinos as massless. Now we know that at least some of them are massive. Now, Duhem would not have been terribly surprised about this because laws of physics are approximate and that sort of thing. However, in contrast to what Duhem says, good sense is not going to get us out of trouble because massive and massless particles are both pretty sensible things. It's not a matter of something weird versus something sensible. It's two sensible things. So what's the bearing of this on the Coleman-Portet critique of conventionality? Well, the point is, here are plausible theories, or at least prima facie plausible theories, that have a non-unique geometry. Well, once in a while, they will mention non-unique geometry as an abstract possibility, which would throw their project into confusion. It's not something they actually take the time to refute, however. It's as if they don't see, they don't think of interesting examples. Now, it seems to me they probably should have thought of Brans-Dicke theory, at least, as problematic. But that's not what they do. And so they claim to have a successful refutation of conventionality. But once we've seen that matter sees this effective conformally flat metric, while gravity sees not only that, but also the flat metric's volume element for the scalar case, and maybe things will be broadly similar for massive spin-2 gravity, the question arises, why, philosophically speaking, should we only stare at the matter field equations? Why not look at the gravitational field equations as well? I mean, don't those count too? And yes, they do. And so to say that gravity is merely whatever matter sees while ignoring ignoring a volume element of all things in the gravitational field equations seems to me to be merely a matter of stipulation. In other words, it seems to fall prey to conventionalism after all, which is what they claim to have refuted. So with massive spin-zero gravity, you have one null coma, you've got two volume elements, which means you can define two metrics, two connections, two projective connections, take the difference and get a gravitational force, observable, gauge invariant, real. So you can make a very nice case for saying gravity is a force in the case of massive spin-zero gravity, and it has no weaknesses in terms of Occam's razor and that sort of thing. On the other hand, you might say to yourself, well, gee, isn't it strange that the matter sector of the theory looks just like Nordström's theory? Maybe I should regard gravity as absorbed into a conformally flat effective geometry. Well, it seems like Poincare's themes of judgment, convenience, and a broad range of possibilities are coming back to mind here, aren't they? So it doesn't seem that we've left conventionalism decisively behind after all, contrary to what they think that they have shown. So once you entertain the real possibility with plausible examples of a non-unique geometry, then their argument against conventionality just doesn't really seem to get going. Once you think about the gravitational dynamics, that no longer seems to work. So Ehlers-Pirani-Schild formalism basically provides a new language to restate the question of conventionality, not an answer to it. Once you look at the kinds of theories that were always the conventionalists' best argument in the first place, or for that matter, a dynamical, constructive sort of explanation along the lines of what Harvey outlined. Those are the sort of theories that make, those are sort of theories that make that kind of philosophy of geometry particularly compelling, and Ehlers-Pirani-Schild does nothing useful to address those examples. Okay, so enough for massive spin 0. What about massive spin 2? Well, what you would expect naively is it's going to be more or less the same story except harder. And a lot of that is true. One of the things that's similar between general relativity and Nordström's theory is you have only one metric that you really need. That plays an essential role classically. And so you might well be tempted to say this is the real geometry. Now, if you want, you can tell a universal force story, and that may well be technically convenient. It's one of the more obvious ways to attempt to quantize gravity in terms of the covariant perturbation theory. Big business in the 70s, doesn't seem to work in that you can't get rid of the infinities, or at least that's what most people think. There are a few people who still think they can do something there. In any case, not demonstrably successful, and pretty serious difficulties have arisen. So. The universal force story is not particularly compelling there. However, once you're quantizing, I think it's a little quick once you're quantizing, because suppose you want to quantize canonically, you want to write down equal time commutation relations, but you don't know which points are at equal times until you know the metric. But the metric is what you're trying to figure out from your dynamics. So you've got a chicken and the egg problem when you're trying to quantize general relativity, which has no analog in Nordström's theory, because in Nordström's theory, the null cone is precisely what doesn't get affected by gravity. So your judgments about universal forces should be robust under what you say about quantization as well. I won't pursue that further, but I think that's interesting. But in any case, a universal force is not the conventionalist best idea, or the conventionalist only idea. It's actually what the conventionalist says when in trouble, when confronted with a theory that has only one observable geometry, that makes conventionalism look kind of odd. Here's the geometry, why are you bringing up something else? It seems faintly perverse, one might think. However, conventionalism really flourishes when you're looking at, or a dynamical explanation for that matter, really flourishes when you're looking at a theory that has more than one geometry, whereas anti-conventionalists are rather reticent to, thus far, to say how they address that sort of theory. I'd be interested to see how one would say that. So I think what one says about conventionality depends crucially on the modal status of the discussion, which is not something which is very often stated explicitly, much less defended in a very good way. So I'm going to say something vague, namely that we should look not simply at our best theory, but at all the good theories. And maybe I'll have something useful to say about what all the good theories are. But I think massive gravities should count. Okay, what about massive spin 2 gravity? Clear roots in Pauli and Fiertz, 1939, continue to be developed by various people into late 60s. Two metrics, two connections, two projective connections, gravitational force. That all seems familiar for massive spin 0. Well, but there are a lot of complications. One of the complications is what you mean by causality gets kind of weird. Now, I think that can be handled, but it's not something that has always been well thought out. Something much more serious is you seem to run into an Assay dilemma. So if you look at, say, the kinetic term for general relativity, you see something which looks like positive energy spin 2 minus energy for spin 0 with the wrong sign. Now in general relativity that's okay because it's just gauge, but with the mass term that thing comes to life unless you manage to get rid of it. So a dilemma arose in the early 1970s. Either you get violent instability from that wrong sign scalar, or you have a discontinuous massless limit for your pure spin 2. That discontinuity, Van Dam-Veltman discontinuity, was the new discovery in 1972, in which case massive spin 2 gravity would be either non-viable because violently unstable or empirically falsified. So that, not much happened between then and dark energy, speaking physically. Philosophically, philosophers often thought they were refuting conventionalism, but really weren't aware of the important things that were happening in the relevant physics. But with dark energy, well, lots of things that used to be settled are no longer settled. And one of the things that became unsettled was whether you could have massive gravity. And there was a breakthrough in late 2010 that seems to allow you to wiggle through that dilemma in a nice way. I could talk about that if that's interesting. Things look pretty good from, say, late 2010 until December. However, Stanley Desser has not been at rest, and having killed massive gravity in 1972, he's got a critique again in 2012 and 13, in that there are interesting causality problems for this sort of theory. So I don't know the answer to that. I don't, there may be ways around this, maybe higher derivatives, people are looking. One of the things that's interesting now is people are actually a lot of people are trying hard to get massive gravity to work. Okay, so to conclude, this stuff was not all settled in 1920. Just look at HEP-TH and GRQC at the Physics Archive to see how non-settled in 1920 it is. Massive scalar gravities make sense, could have been true. Conventionality looks good. Massive spin 2 gravity, maybe, I don't know, stay tuned. But we need to think carefully about what collection of theories we are talking about or should talk about when we are doing the philosophy of geometry. Thank you.